So, hello everyone. Today I'm going to talk about a quantitative chemical analysis about gravimetric and combustion analysis. So here is my table of contents. First, we'll be talking about gravimetric analysis, of course, and then the calculations of gravimetric, then the precipitation, thermogravimetric analysis, and lastly, combustion analysis. So let's jump right ahead. So first, before we delve into the calculations of gravimetric analysis, let's first identify the word gravimetric. So what do you understand from the word gravimetric? Okay, so the word gravi is from the derived from the word Latin called gravis, and gravis means heavy or weighty. And when something is called heavy or weighty, it is associated with mass. And metric is for measuring, assessing. So in simple terms, gravimetric analysis is measurement of mass. And a precise term, gravimetric analysis is a technique that involves precise measurement of mass changes, usually the product, to determine the concentration or amount of an analyte in a sample. So here, why don't you try a problem here? So in this problem, it says a 10 ml solution containing chlorine was treated with excess silver nitrate to precipitate 0.4368 grams of silver chloride. What was the molarity of chlorine in the unknown? I think this is supposed to be a chloride ion. It's not supposed to be chlorine gas. Anyway, that's my mistake. So So before we solve it, I have here 4 basic steps into gravimetric stoichiometry. This is not all of the steps, but you usually use this in solving gravimetric problems. So here are the 4 steps. So first of all, you have to write out the balanced chemical equation. As much as possible, you write out the balanced chemical equation. And the second, write out the known information, like the molar mass, molar mass, and everything else. And the third is convert moles to grams and vice versa. And fourth, determine the number of unknown moles using mole ratio. So let's do the problem. So here, as you can see, here is the chemical equation. Do you think this is balanced? And the answer is yes, the chemical equation here is balanced. So here's the reaction. As you can see, the silver chloride is the one that precipitated. So of course, like I said, you write out the known information first. And here you're finding for the chloride ion, the molarity of the chloride ion. So here's the stoichiometry. So 0.4368 grams of silver chloride times 1 mole of silver chloride over 143.32 grams of silver chloride. So where did I get the 143.32? Where do you think? So the 143.32 grams is from the molar mass of the silver chloride. So you cancel out the grams AgCl, and then you get 3.048 times 10 to the power of -3 mole silver chloride. And if you look at this, the mole ratio of silver chloride with chloride ion is 1:1. So the mole of chloride ions is also 3.048 times 10 to the power of -3. And then of course, like in the problem, there's also 10 ml solution. Of course, you convert that to liters because that's a molarity. So mole over liter, and then you'll get the molarity. So if I'm talking too fast, I will explain on the next slide as detailed as possible. Right here. As you can see, there's another addition of 1 mole. So why did they add that? You'll see why. So here, you cancel out the like terms, the gram AgCl, to get the mole. Of course, you had to convert to mole first. And then to get the mole chloride ion, you have to cancel out the mole AgCl. And now you have the mole chloride ion. And then you divide that with the liter. Then you get the molarity of the chloride ion. So now we're moving on to the second problem. So it says here, how many grams of bromide ion were in a sample that produced 1 gram of silver bromide precipitate with the formula mass of 187.77. In this case, formula mass could be the same with molecular mass. They're not the same, but in this type of problem, they're technically the same. So I'll give you a second. So what do we do first? We write out the balance equation here. Okay, here's the balance equation. Since it's similar, it's like exactly the same with chloride ions, except chloride is replaced with bromide ions. As you can see, AgBr is your precipitate. And here, the known information is 1 grams of silver bromide, and you're looking for the bromide ion. And then we use stoichiometry. So 1 gram AgBr times 1 mole silver bromide over 187.77 grams. That is the formula mass of silver bromide, reacting with 1 mole, not reacting, but times with 1 mole bromide ion over 1 mole silver bromide. And then you get, and then you have this one, the grams is from the bromide ion. You can get it from the periodic table and over 1 mole bromide ion. So here's the cancellation of like terms. So you first cancel out the grams to get the mole. And of course, you have to cancel the mole to get the mole of bromide ion. And then next, cancel out the mole bromide ion to get the grams. And then the answer. Your answer should be 0.425 grams of bromide ion. And here is probably the last problem. Okay, so it says here how many grams of silver bromide would have been formed from 0.1 gram of radium bromide. So let me give you you can pause this video first. All right. So like I said, in the basic steps, my 4 basic steps, you have to balance the equation first. So here, radium bromide reacting with silver nitrate. And you have to see if this is balanced. Does this seem balanced to you? And in fact, it is. It is balanced. Okay, so the known information is 0.1 grams of radium bromide, and you're finding for silver bromide, the grams of silver bromide. Excuse me. So here's the stoichiometry. So first 100 grams of radium bromide times 1 mole of radium bromide over 386. So where did I get this 386 grams? It's from the molar mass of radium bromide. And then you times that with 2 mole silver bromide over 1 mole. This is the mole ratio of silver bromide and radium bromide, as you can see in the chemical equation. And then you react with, I keep on saying, and then you times it with 187.77 grams over 1 mole silver bromide. And of course, like you cancel the like terms, mole, cancel out grams to get the mole, and you cancel out the mole of radium bromide to get the mole of silver bromide, and you get cancel out the mole of silver bromide to get the grams of silver bromide, and then your answer should be 0.097 grams of silver bromide. So now let's talk about precipitation and identifying techniques and the overall overview of precipitation. So what do you know about precipitation? So precipitation, and in the precipitation, there are precipitates. Precipitates are insoluble ionic solid products of a reaction formed when certain cations and anions combine in an aqueous solution. So here's the diagram of how a precipitation forms in a solution. So first, of course, this is the aqueous solution, the green one, the one on the far left. And then it will have suspension, and then it will have this supernatant fluid and the precipitate collecting at the bottom. This is just a simple diagram of a precipitate. As there are factors considering precipitation, like how, why, and what. So like how to initiate crystal growth, what techniques to use to yield better crystal growth or precipitate, and what are the factors to consider in crystal growth. And that is what I'm gonna be discussing in my next consecutive slides. So you can initiate crystal growth by supersaturated solution, and that is just one of the ways. So supersaturated solution is when the concentration of solute predominates the equilibrium solubility. So I said one way because you can have you can initiate crystal growth by sublimation, by the difference in pressure, and just by reacting reactants together, and you have a crystal growth. But my focus for today is supersaturated solution. So there are two stages of crystallization. First one is nucleation and particle growth. So what are those? So nucleation is the initial step in the formation of solid particles from a solution or a vapor phase. It involves the aggregation or the clumping of individual molecules, ions, or atoms to form small clusters or nuclei that serve as the starting point for the growth of larger particles. And on top of that, the particle growth proceeds afterwards. So particle growth is the subsequent process in which the nuclei or small clusters formed during the nucleation increase in size by the addition of more molecules, ions or atoms. This results in the development of larger and more well-defined solid particles. So here are the key differences in nucleation and particle growth. So nucleation is the initiation of the solid phase. Can occur spontaneously when the concentration of solute molecules or ions in a solution or vapor exceeds a critical value, or it can be induced by external factors such as the introduction of seed crystals or changes in temperature and pressure. So particle growth follows nucleation, like I said, and involves the progressive addition of solute species onto existing nuclei or particles. It does not initiate the formation of the solid phase, but rather enhances and extends it. Okay. So there are techniques that promote particle growth. The first one is by raising the temperature to increase solubility and thereby decreasing supersaturation. Here, if you decrease supersaturation, you will have purer and larger crystals. And the second one is by adding precipitant slowly with vigorous mixing to prevent local highly supersaturated. That's what you're trying to avoid, is to a supersaturated condition where the stream of precipitant first enters the analyte. The third one is using a large volume solution so that concentrations of analyte and precipitant are low. So I'm going to be talking about homogeneous precipitation. So what are those? So homogeneous precipitation is a chemical process in which a solid precipitate forms uniformly throughout the solution without the formation of distinct solid particles or clusters. In other words, the solid it forms is evenly distributed at a molecular or microscopic level within the liquid phase. So it is often performed under controlled or slowed conditions. So to form a homogeneous precipitation, you have to perform it in slow conditions. Excuse me. For increased impurity, avoidance of agglomeration of particles, and the particle size control. So as you can see here, there are two beakers. Which do you think here is the homogeneous precipitation? Is it the left one, the orange precipitate, or the right one? So the homogeneous precipitation is on the right side. Here, the precipitate appears to be more larger than the precipitates of the left side. So the right side is the homogeneous precipitation. So I'm going to talking about the coagulation of a precipitate in the presence of an electrolyte. So what does this mean? It refers to the process of precipitating ionic compounds. So when you say coagulation of a precipitate, it usually refers to ionic compounds. So in the presence of a compound that dissociates into ions when it dissolves, this electrolyte helps in the coagulation or coming together of tiny colloidal crystallites into larger crystals. So this is how it looks like. As you can see, the red dots are the chemically adsorbed silver cations. This is it is absorbed in the primary absorption layer, and then the secondary, you call this the ionic atmosphere or the ionic boundary atmosphere. So due to the silver cations, it is attracting the anions. As you can see in letter A, it cannot go together because of the repulsion of the anions. And for them to coagulate, there are two ways. One way is by heating to increase the kinetic energy, and the second one is by the presence of an electrolyte. And in the presence of electrolyte, you can increase the concentration to form this coagulation before it comes down. Okay, so here are the terms for precipitation. So the mother liquor is a liquid from a substance that precipitates or crystallizes. As you can see in the diagram on the left side, the mother liquor is there, the beaker on the top. And digestion is a process that promotes slow recrystallization of the precipitate. Particle size increases and impurities tend to be expelled from the crystal. So digestion involves reheating the solution, often near its boiling point, and adding a small amount of fresh solvent to it. The purpose of this step is to redissolve the initially formed crystals. So the purpose of digestion is to form a much purer crystals. There are three types of impurity that affects crystal purity. The first one is absorbed impurity. When you say absorbed, it is attached to the surface of the crystal. Absorbed inclusion impurities is there are small foreign substances such as gases or liquids that are trapped within the crystal lattice of a solid material. These inclusions become incorporated into the crystal structure during its growth. And absorbed occlusion impurities are larger foreign particles such as mineral fragments or solid inorganic materials that are enclosed within a crystal or mineral, but are not part of the crystal structure itself. So there, that is the key difference. In occlusion impurities, there are foreign particles that are not part of the crystal structure. But in inclusion, it is part of the crystal structure. So in occlusion impurities, the particles are physically trapped within the crystal lattice. So here you can see in inclusion, within the crystal lattice, you see it grows to become like a crystal. In occlusion, it's a large foreign particle. And it says here it can also contain a solvent. So now I'm going to be talking about peptization. So peptization involves adding a peptizing agent, like an electrolyte, to the coagulated system. The peptizing agent disrupts the aggregates, causing the particles to return to their dispersed colloidal state. So this is kind of wordy. So in simpler terms, it is the resuspension, reconversion of colloidal particles. So why is this needed? So peptization is for evenly distribution of the particles throughout the solution. So here on the left side, this is an example of a stable colloid. As you can see, it's evenly distributed throughout the solution. And on the right side, this is an example of unstable colloid. See, there's aggregation. You're trying to prevent that, and then the sedimentation. And here is the simple diagram of peptization. So as you can see, the iron hydroxide precipitate settles the bottom. And then when you add a strong electrolyte like iron chloride, and then shake it vigorously, it will form a colloidal suspensions, and then it will be evenly distributed throughout the solution. Thermogravimetric analysis. So what is hygroscopic substances? You may have an idea, but if you don't worry. Hygroscopic substances are substances that has the ability to attract water or moisture from the air. So why is this related to thermogravimetric analysis? Thermogravimetric analysis quantitatively assess moisture content, investigate thermal behavior, and provide insights into how these materials interact with moisture at different temperatures. So that is the relationship between thermogravimetric and hygroscopic substances. Remember that the final product of any gravimetric analysis, the product should be pure, insoluble, of a known composition, and it is easily filterable. So here is the reaction. As you can see, towards the end, you form calcium oxide, which is a known composition. And here is the curve for the gravimetric analysis of the substance. You see the mass loss as you increase the temperature. Now let's go on to our last topic, combustion analysis. So combustion analysis is used for determining carbon and hydrogen in organic compounds burn in excess oxygen. So here is an example problem. So a compound weighing 5.714 milligrams produce 14.2014 milligrams of carbon dioxide and 2.529 milligrams of water upon combustion. Find the weight of C and H in the sample. So 1 mole of carbon dioxide contains 1 mole of carbon, and this is usually in the chemical balance equation of combustion analysis. So as you can see in carbon dioxide, the ratio for carbon is, you see, is 1. So first you get the moles of carbon in sample of carbon dioxide, and remember that carbon dioxide with carbon is 1-to-1 ratio. So whatever you get, the amount of mole you get for carbon dioxide, you also have it the same for the mole of carbon. Okay, and then you times it with the mass of carbon to get your mass, to get your milligram mass. And then since it's finding for the weight percentage, put in this for formula. So now you find for hydrogen. So here, since 1 mole of water contains 2 mole of H, the moles of H in sample equals to 2 moles of water produced. So here is the answer. You get the mole, and then get the mass of the hydrogen in sample, and then you get the weight. Thank you for watching and listening.